Good morning. Welcome to the 2017 Charm++ workshop. I guess it's a little bit early on a Monday morning, so I noticed a few people that I expect to see here are not here yet, but the show shall begin. Writing down that 2017 workshop and looking at the website, this is the 15th workshop, made me aware of it, that is the 15th workshop, a series that began not in 2001, 2002, it switched from being a fall workshop to a spring workshop somewhere in the middle, where we kind of skipped 6 months. So that's how it gets to be a 15th workshop. If you go to the website, you will find all of those workshops there. In fact, talks and their abstracts, and in many cases, the actual PowerPoints and maybe even videos will be found there. So someday, if I either want to feel nostalgic or I want to feel guilty about taking this long to do the same the thing, I should go look at every one of those there. But then that made me reflect a little bit on the history. The Charm++, that name is from a 1993 paper. That's 24 years ago. So although some people say the language of the future will be who knows what it is, sequential language, but we know it will be called Fortran. So in some sense, the Charm++ name stayed, but we might have but the language itself evolved quite a bit. What we call chars were there before, even in 93 or even before that, but the char arrays and the rest of the language has evolved after that point. And so maybe somewhere around 2001, 2002, with Orion Lawler's thesis, and around that time with work of several other contributors to Charm++, the language kind of solidified in terms of foundational concepts by 2002. That still leaves 15 years. So 15 years after, what have you been doing? So this is depressing in some ways. Say, hey, maybe I was just too slow. And I say I because I'm the kind of the constant. All the great grad students have come and gone and moved on into their career. So it's my management and my direction that's must be at fault there for the speed. And there is some truth to that, no doubt. But I think I prefer the other interpretation, which also has adequate truth in it to make me want to believe it, which is that we have been doing a long co-design cycle. We have been enhancing and adding features based on all the large-scale applications that we have been developing. Originally, it was NAMD, but then also Changa and OpenAtom, and then several other collaborations from outside. And every one of them makes us rethink the features, makes us add something new, change something. And so that co-design cycle is long. It just so happens to be long. I'm not sure in complete 2020 hindsight one could have designed everything in the first 5 years after 2002, but I think that's not feasible. You get to tune yourself to real life applications by actually working on real life applications. The other thing is the foundations were done in 2002, but the fleshing out, that just meant that adaptive runtime ideas were there, but to actually make the runtime adapt, there was a lot of work, research as well as engineering that need to be done. And so that it turns out that the research agenda opened by that simple idea that I'm going to come to in a minute, the basic ideas of Charm++, turned out to be a vast research agenda. So those are my rationalizations, excuses, or maybe reasons for taking this long. But we are in a very good place now. I was talking to Mike at dinner yesterday, and I think we kind of have come to the point where Charm++, after all those years, has concepts, and the rest of the world, which is the technology, the machines, and the application sophistications, is finally in a place where this is useful. So no matter the duration, we are in a good place. So I traditionally do this talk where for the new people, I introduce Charm++ the foundational concept very briefly, so the rest of the workshop makes sense. And then I will have some highlights from the last year, and then challenges for a future, and then a little bit of a overview of the workshop. So Charm++ is not an alternative to C or C++. It's an alternative to MPI or UPC and so on. And it represents a style of writing programs and the adaptive runtime system and the whole tools ecosystem surrounding it. And the three design principles are, I'll enumerate them here. Overdecomposition. This is the idea that we let the programmer decompose the computation into work and data units into many more pieces than there are execution units. These might be cores or these might be nodes, depending on how you want to structure your solution. And so that's the first thing that we do that empowers the runtime system. Another thing that empowers the runtime system is we allow these work units to be migratable across processors. We do that by saying the programmer shall not refer to the processor when communicating with these objects. They refer only to the logical entity, the object. And so the runtime system, if it moves it from one place to the other, if the global name of that object is the same, since the global name is the same, the programmer doesn't have to know that it moved. Their program remains the same in spite of the migration. The runtime system to make this work has to do some gymnastics underneath, but that's better. It belongs there and it can do it efficiently. And a consequence of that almost, but not quite, that is to say, one could just do these two things and not do a message-driven or asynchronous runtime system, but it's a very natural thing when you have overdecomposition to notice that on every core there are lots of objects. What's going to execute next? That question can have two answers. One is let the programmer decide, and the other one is let the runtime decide, and we choose the let the runtime decide answer, and that gives us a message-driven execution. It's also these days called data-driven execution or task models and so on that have become very popular terminology now. That's all comes from the message-driven scheduling. So in Charm++, these concepts become more concrete in terms of chars. Chars are these overdecomposed entities, and a char is nothing but a C++ object which happens to have a couple of special things. One is it has a globally valid name, not a pointer, but a globally valid reference. And the other one is that they have methods designated as entry methods that can be invoked from any other processor, from anywhere in the system, asynchronously. And these chars are then organized into indexed collections. So a program may consist of a large number of collections, and each collection may have its organization as a one-dimensional or five-dimensional or sparse or contiguous set of collections. And then these chars communicate via asynchronous method invocation. Just pictorially, once again, to repeat the point, you have a collection of objects of your program. Some of those are globally visible. Let's call that a parallel object space. And the others are owned by one of these objects in the globally visible space. Exactly one, so that they migrate with, the owned objects migrate with their parent object. These objects are partitioned to processors by the runtime system or assigned to processors, and the scheduler exists to mediate communication between them and decide who gets to run next. And then the scheduler, the way it works is that if this object wants to invoke a foo method on A23, the runtime system packetizes the method invocation, figures out which processor it is on, puts it in the scheduler. At some time in the future, that scheduler picks up that message and identifies the object. If it has not migrated away, invokes the method on it. And that method runs to completion, doing the same kinds of things that the other orange object did. So this is the basic execution model in a nutshell for the Charm++ program. As programs execute, some objects are observed by the runtime to be heavier, some lighter, who talks to whom, all of that the runtime can keep track of, and therefore using that it can migrate those objects around. So this asynchrony, overdecomposition, migratability, the foundational ideas of this model. And with that, if you add into the runtime system some introspection, since it's observing the cues, since it's mediating the communication, it can do introspection if you do that. And if we add adaptive strategies, then we get an adaptive runtime system. And with that adaptive runtime system, you can do a variety of things such as load balancing and communication optimizations and its prefetching and fault tolerance and so on and so forth. Some of these things you'll hear about in the talk, and some of these you should read if you don't already know. The production applications using Charm++, the set is growing significantly. There are more applications that are not listed here that are under development. And so I would say in the last couple of years we have got a good good growth in outside applications. By outside I mean not directly funded along with us. And so that's a good sign for the growth of Charm++. What's the relevance of Charm++ to Exascale? Well, it turns out the intelligent runtime system, which is developed originally for handling applications variability, right? Dynamic variability. That was our original motivation. It turns out to be useful for handling challenges of Exascale hardware, which also include variability or dynamicism in the hardware and more sophisticated applications, more multi-module applications, and so on. So specifically, 4 things in addition to the dynamic load balancing that's automated in Charm++ and the data-driven execution that gives you the task-based models and so on, those are definitely useful at Exascale. In addition to those, Charm++ has support for resilience. There are multiple approaches for that: in-memory checkpoint approaches, leveraging non-volatile memories, a really scalable message logging protocol that has a novel parallel restart, which is useful for a really low mean time between failures. But engineers keep pushing the need for that further in future. And all of these approaches leverage the object-based decomposition in some essential ways. We have quite a bit of work on all of power and thermal optimizations that again rely on the ability of the runtime system to migrate objects and to control individually the individual nodes or cores power consumption and deal with the load balancing issues that arise. There are probably a dozen papers on each one of these 2 topics. There is a capability in Charm++ to shrink and expand the sets of processes allocated during execution. And then more recently, well, actually a couple of times we have done work on adaptivity-aware resource management, like doing the whole machine optimization by job scheduling and resource allocation with the capability that we know that we can tell this job to shrink or to expand and to use this much power or that much power. So with all of these things, actually, there are some good papers about it. A very high-level summary paper was published in IEEE Computer during the last year, which hopefully gave it some visibility, which says power, reliability, and performance, one system to rule them all. The system being, well, what was it? Anyways, so this actually summarizes. If you want to go look at the overall summary of the work in all of these areas, this would be a good kind of very light reading paper, and then you can go to the other papers from there. I'll skip this slide. One issue that we have been making sure to deal with recently is interoperation with MPI. So you can have an application that's in MPI and insert a Charm module into it, or vice versa. And that can happen either in time sharing mode, run Charm module, run MPI module, run Charm module, run MPI module, or space sharing, different processors doing different things, or mix them up. So all of these are supported, and the support for features for that support are being enhanced. I will just mention, I think I had mentioned this before, that there's been support for loop parallelism. There is a CK loop construct in Charm for many years. We are enhancing that, but we are also doing a new integration with OpenMP. We finished GOMP based one last year, and we are doing an LLVM based one now. And there are other ways of integrating other people's schedulers in Charm++, such as some collaboration with Barcelona folk. So I will skip this picture. So a couple of recent developments. Charmworks is supporting Charm++ commercially. We have a couple of SBIR grants in progress, so I thank DOE for those. And nonprofit use of Charm++ still remains free as ever. And Charmworks, whatever improvement it is making, are being brought into the university distributed version. So far, we have not forked the code, and we have no intention of doing that now. Now, the improvements have included, well, anyways, let me not list the improvements. In the evening sometime, we will talk about the new features, where we'll talk about 6.8 and other things like that. We may get to that topic a bit. The more recent project at Charmworks is some funding for making adaptive MPI more robust and improving it. And so that's a project that's continuing as well. So I think I'll take a minute or two to list these challenges. These are actually long topics, so it's very easy to get engaged in long discussion. Some of these are opportunities, some of these are things where we have already done some things. The fact that there are fatter nodes, including KNL and that variety of processing, but even otherwise, large number of cores on a node is one type of a challenge, and we have solutions for that. We can in many situations, having just chars bound to individual cores works fine, but when overdecomposition has a significant cost, you might want to bind chars to a node and then use some kind of other different way of dealing with parallelism inside a node. We are pursuing both of those. Heterogeneity and load balancing interaction, you'll hear some talks about that. That's another challenge. HBM, high bandwidth memories of various sorts, and other memory hierarchy complexities, another. I think with prefetch capabilities in Charm, we are reasonably well equipped to deal with that. Fine-grained execution has become a new challenge for us with some of the applications that we have looked at recently, and various optimizations in the runtime are aimed at that. Ability to fire subscale simulations and doing multiple simulations simultaneously with resource requirement shrinking and expanding is another thing that we need to pay more attention to. In situ analytics we are really a good opportunity to do in situ analytics compared with something based on MPI, because after all, we can interleave the execution of the analytics and main program. So I think these are some of the things that we would be paying attention to. And of course, funding is one more thing that we need to pay attention to. So we'll see. It's one of those things that waxes and wanes, and Charmworks is in some way an attempt to create another thing which doesn't wax and wane as much, hopefully. So now coming to the workshop, we have an excellent program. We have keynote by Michael Norman today and Rajiv Thakur tomorrow. We have talks on capabilities in Charm++ and algorithms. We have talks on stuff built on top of Charm++. Dharma and Greenmal, no, HPX is not built on Charm++, but there is a talk on a language issue there as well. And then there's a bunch of application talks as well. So I'm looking forward to listening to all of them. There's a panel on how the Exascale, Rajiv being the Exascale software person, and many of us here are interested in Exascale. And at the same time, we're looking at the medium range 10 node, 100 node, 1000 node type penetration in the broad HPC, broad manufacturing engineering industry, whether that's happening or not, and whether Exascale can help with that or not. That's the topic of that panel tomorrow afternoon. So once again, welcome you all to the workshop. Thank you for coming here, and hopefully we have an excellent discussion today and tomorrow.